This is the Tech Talk for Eddy Braking System for Supersonic Missile Testing. The development of this technology is in the context of the Supersonic Naval Ordnance Research Track in China Lake, California. We will refer to this facility with the acronym SNORT. The principal investigator for this project is Tony J. Morris, the founder, president, and CEO of American Maglev Technology of Florida, more commonly referred to as AMT. For nearly 30 years, AMT has been about the business of putting magnetics to work for humanity. Our core competencies are high-fidelity modeling and simulation, continuum electromechanics, and multidisciplinary project management. We believe that not one expert can know everything, so we build and fortify our professional relationships with teams comprised of an eclectic group of industry leaders and scientists who work together in synchrony. This project brings together one of the world's foremost magnetic field theoreticians, IEEE Fellow Dr. Kent Davey, and Dr. Lakshmi Sankar, Sikorsky professor at Georgia Tech, a recognized expert in computational fluid dynamics and supersonic aerodynamic modeling. Our end goal is to take the know-how developed in projects like this one and spin it out into new focused enterprises that seek to commercialize new solutions in defense and commercial markets. We are proud to be a link in the chain that connects ideas with true commercial innovation and market opportunity. The existing high-speed test setup has been in place for a long time. Missiles are called upon for higher and higher speeds and more capability, making the testing of these new technologies even harder to manage. The Navy has been well served with the current solution that uses a water displacement braking system, which is basically a small lake to splash the sled into. It works functionally, but at a huge annual cost in maintenance and readiness and reliability. A passive solution is needed and desired by the SNORT team that would stand up to all the rigors that the active system deals with every day. The new solution should not require any outside inputs or consumables and fit in the current braking envelope using existing test sleds. Any changes to the system, which in this case include the installation of a magnet array on the test sled, should not result in a major change in the braking profile or increased drag penalties. What is at stake adds up to a lot of money, a lot of time spent on maintenance, and also peace of mind that the test sled, regardless of mass and at velocities approaching Mach 1, will brake to a stop without damage. We also expect to scale up the system beyond Phase 2 to address hypersonic speeds. The estimated brake maintenance cost per year at SNORT China Lake is estimated to be $12,000. This concept could also be applied in other high-speed test track operations that are currently part of the day-to-day work scope for SNORT. Eventually, the magnet arrays can provide not only the braking, but also the acceleration without rocket motors, rocket fuel, and controlled explosions. It's called cold launch, and it's a subject for another day, except to say that together, this represents a huge and growing opportunity for our team to serve our greater Navy clients, a few of which are listed here, including Naval Air Warfare Center Aircraft Division Lakehurst in New Jersey, Holloman High Speed Test Track in New Mexico, with whom we've already had discussions, Eglin Air Force Base in Florida, Hurricane Mesa Test Track in Utah, and Sandia National Laboratories in New Mexico. Here is a rendering showing how the rocket test sled gets retrofitted in order to integrate our solution. It conforms to all the Navy's stated requirements for size, reliability, and cost. A magnet array built into a carbon composite fin is attached to the sled as you see here in this rendering. A series of steel trusses is installed into the braking section of the track, which induces braking eddy currents when the magnets pass by. The concept has been optimized and simulated for thousands of missile test operations in all sorts of operating conditions, and we are confident that we can stop a 1-ton test sled traveling at Mach 0.5 in less than 300 feet. In simulation, this works, but we know that simulation only goes so far. A full-scale prototype is currently in production for testing at SNORT beginning in mid-2023. Based on all this, the technology readiness level stands at 4. The original Phase 1 contract was awarded in 2020, and we have since been awarded the Phase 1 option and Phase 2 base program for full-scale testing of this concept. As of the date of this recording, we are building 50 feet of braking trusses for installation into the trench between the track rails at SNORT. The magnetic fin will be retrofitted into a test sled at full scale and will be capable of stopping a 1-ton test sled traveling at between 100 and 200 feet per second. In 2024, our team will expand the track to 250 feet, which will be capable of braking a sled traveling at 650 feet per second, which is the current maximum capacity of the water brake. Assuming favorable results, we will look forward to deployment as this testing is successfully accomplished by the end of 2024. Beyond 2024, we believe that the track can be further extended to provide braking capabilities for hypersonic speeds. Key features of the system are listed here, with the advantages of the AMT system shown in the blue column on the right-hand side. A solid-state magnetic brake that interacts with steel trusses will replace a high-maintenance water brake and pump system located in the underground vault. Our system requires no water at all, which lifts a major regulatory burden for the SNORT facility. Annual O&M and permitting costs would be avoided, and the potential capability of the braking system would be greatly expanded to Mach 1 and beyond. The system components fit into the existing sled and track and minimize the amount of setup time required to run the missile tests. While removing the water braking system and adding magnets to the sled does add additional weight to the test article, the enhanced braking forces provided by this technology appear to offset any additional drag forces, rendering the added weight largely inconsequential. We do expect to seek Phase 2.5 funding as our testing program concludes in late 2024. This will include the extension of the track beyond 250 feet for higher speed military standard testing, which would elevate the TRL to an 8 or a 9. While the test system at SNORT would technically be the first installation of a full-scale system, we would expect 3 to 5 years of government review prior to full implementation across the Armed Forces' other test tracks. In addition to our primary transition advocate at SNORT, we expect to work with the nation's other high-speed test tracks under the leadership of the Tomahawk Weapons Program Office. This specific application is uniquely tailored to the nation's high-speed test facilities. However, it has the potential to open up many new opportunities at these locations, both in braking from hypersonic speeds as well as the promise of cold launch technology to replace rocket motors. In commercial and industrial markets, the holy grail of braking is for brake surfaces that don't wear out. Magnetic fields need no new brake pads, no oil and grease, no electricity, and no hydraulic fluid. Together, eddy current braking and cold launch represent a huge growth opportunity across multiple sectors, both inside and outside the Department of Defense. The elegant solution we have proposed is simple, but it represents a multidisciplinary approach to stopping a missile test sled. It is a novel deliverable based on a unique understanding of continuum electromechanics, bringing magnetic fields into service to create more than 60,000 pounds of braking force, with no requirement for power from the electrical grid, nor a suite of highly precise and fast position and velocity sensors. Everything works passively, with nothing to chance or to fail. Through Phase 2 and beyond, we will interface with the Navy to identify funding sources and customers who can help us bring this technology from full-scale prototype to commercial innovation. Our own proven strategy is to spin these innovations out into new U.S. companies with their own focused management teams, just as we have done with Emergy and Inductive Ventures. You can check out the links for these companies at the bottom of this page. If we've learned anything over our 30-year history, we know that high-quality, committed partnerships in strategic alliance are the key to progress. We're seeking manufacturing, implementation, and testing partners for whom this technology might be a good fit. Our information is shown here. Please reach out to us anytime. We also plan to be in attendance at the NavAir and NavSea Innovative Technology Showcase in Washington, D.C. from March 14th to 16th, 2023. If you'd like to meet with us, please send us an email. Thank you for your interest.